Hello and welcome to this video for Chemistry 20. In this video, we are going to do the first lesson of the solutions unit. So we're going to talk about what a solution is, as well as we're going to get into learning how to calculate the concentration of a solution. So first of all, when we have matter, it can be classified as either a mixture or a pure substance. Pure substances are elements and compounds, whereas mixtures are when you have multiple elements and compounds together. And a mixture can fit into two categories, either a heterogeneous mixture, which are things like mechanical mixtures and colloids, or a homogeneous mixture, which is where our solutions fit. So we're going to briefly talk about those and the differences between them and how you can identify when you have a true solution. So first of all, matter is defined as anything that is solid, liquid, or gas, has a mass and either its own volume or takes up the volume of its container. A pure substance has a definite fixed composition. So what that means is, for example, hydrogen. When I have hydrogen gas, I know it's always H2, right? When we go back into the science 10 naming elements. And so it's always two hydrogens to make up hydrogen gas. If I were to change that, it would become a different substance. Same with something like a compound of water. Water is H2O2. If I were to add another O to that to make water is H2O. If I were to add another oxygen to that to make H2O2, that becomes hydrogen peroxide, a completely different substance. Okay, so elements and compounds, when they're on their own, they are pure substances, and they have, again, these definite fixed compositions. Whereas a mixture, you can have any kind of amount of them being mixed together. There's no definitive amount that has to be together, and they can be separated by physical means. We'll talk today about some ways of separating mixtures. Now, getting into mixtures, the two main categories of mixtures are heterogeneous mixtures and homogeneous mixtures. Okay? A heterogeneous mixture is sometimes also called a mechanical mixture, where the components are visible. Okay? So either they're very obviously visible, like this mix of candy here, or it could even be a colloid. Now, a colloid isn't necessarily something that looks visible, but it is a cloudy mixture. And the reason you have it being cloudy is because there's solid particles that are being suspended throughout. If it's a liquid mixture, you have solid particles being suspended in the liquid. And so you can see those solid particles, which is making it look cloudy. A true solution not only is uniform, but you cannot see any components. So it has to be clear or transparent. It can have a color. Some of these solutions have a color. If they don't have a color, we call them colorless. But clear represents the fact that we can see through them. They are transparent. Okay? Sometimes a solution or a mixture at first may appear homogeneous when you're looking at it with the naked eye, but then if you magnify it, you can start to see the particles. If you can see particles, that means that it is a heterogeneous mixture, not homogeneous, okay? In order to be homogeneous, no matter how much you zoom in, you should never be able to see particles. Excuse me, because in a solution, you have a substance that is completely disappearing inside of the other substance. And so the two substances that make up the solution, the first we'll talk about is called the solvent. The solvent is the dissolver and is always present in larger quantity. So if you have a mixture and you're told I have 10 milliliters of substance A and 5 milliliters of substance B, substance A with a greater amount will always be the solvent. Okay? The most common solvent that we have is water, and a lot of our solutions are made in water. But it doesn't always have to be water, and it doesn't always have to be a liquid either. The other part of the solution is the solute. The solute is what is dissolving. So let's say we're making Kool-Aid or salt water or sugar dissolved in tea. Those are the solutes. Okay? That's the substance that is being dissolved in the solvent. Now, what kind of solutions can we have? So as I mentioned, it doesn't always have to be a solid like salt dissolved in a liquid like water. That's one of our most common solutions, but it could be a solid, liquid, or gas in various different phases. So I could have a liquid in a liquid, which is what antifreeze is made out of. I can have a solid in a liquid, like Kool-Aid. I can have gas in a liquid, which is carbonated beverages, where we dissolve carbon dioxide in a liquid. A solid in a solid, which is how we make metal alloys. We obviously melt the metals first so that they can mix together, but then they resolidify. You can have a liquid in a solid. You can even have, I don't have on here, a gas in a gas. That's a mixture of the air around us, where nitrogen in the greatest quantity would be the solvent, and the oxygen and other gases would be the solute. You can even have a gas in a solid, like making styrofoam, for example. Okay? An aqueous solution is a solution that is where water is the solvent. So sometimes, remember back in our review of Science 10, we would write the formula for a compound, and then we would check our solubility chart, and if it was soluble in water, we would write aqueous. And so that's what aqueous means. It means it's dissolved in water. Okay? Water is known as the universal solvent because most of the compounds, or not compounds, sorry, most of the products that we have out there that are mixtures are usually dissolved in water, which is good, but can also be bad. 75% of our earth and our bodies are made of water. And when you make a solution, again, remember the solute disappears in the solvent. So you cannot tell sometimes that you have toxins dissolved in the solution. Now, how can we separate a solution, or how can we tell whether or not, again, we have a true solution? So first of all, when you have a true solution, you cannot separate them by filter paper. With a heterogeneous mixture, you can separate them with filter paper unless they're a colloid, because colloids, the particles are so small that they actually still travel through the filter paper. But most of the time, a heterogeneous mixture will get trapped in the filter paper, the particles, the bigger particles, and then the solvent, or whatever, if it's a liquid, will go through the funnel. Also, there will be no scattering of visible light if it's a true solution. If you have a colloid mixture, so again, it may appear that it's a solution, you can't see the particles, but when you shine light through it, if they scatter, the light beam gets bigger. That means it's actually a colloid, not a true solution. A true solution, the light just shines right through and it doesn't scatter. So how can we separate, if we can't use filter paper, how can we separate a solution? We can do it through the different intermolecular attractions among the components. So chromatography is one method. In chromatography, you take little strips of something. You can use something called chromatography paper, but you could also just use filter paper. And that filter paper gets dipped in the solution in the very tip of the solution, and then the components travel up the filter paper based on their attraction to the filter paper. Okay, usually the filter paper is polar, and so it has to do with like and like attracting. So the non-polar substances travel higher because they're not being attracted to the paper, whereas the polar substances get they stop sooner down because they are being attracted to the paper. Okay, so it's based on polarity that chromatography paper works. Distillation. This is an example of distillation. This is usually how you separate a liquid from a liquid. You have a heat source, like a flame, over your mixture, and whichever liquid has a lower boiling point is going to evaporate into a gas first, and then it travels through this tube called a condenser, where liquid water or colder water is pumped around the surrounding of the tube, which makes whatever that gas was turn back into a liquid, which drips down into a separate container. So it separates the two liquid, the solute and the solvent. Whichever one has a lower boiling point will boil first. The second one will be left separately. We can also separate, let's say I have a solid solute, solute was the right word. If I have a solid solute in my liquid solvents, I can evaporate the solvent. If my solvent is something like water, say I have a mixture of salt water, okay? I have some type of an ionic compound. Ionic compounds, remember, are always solid before we put them in water. And so if I want to separate that, I can evaporate away the water and I'll get left with the solid crystals. And there's actually a lab that we do in Chem 20 to separate a solution of sodium chloride where we evaporate the water to get left with the solid crystals. Okay, so those are some separation techniques, whether we evaporate, distill, or use chromatography to separate the different components of a solution. So solutions in our society, most products that we have are solutions. It's not very often that you have something that's pure. Even water, our tap water, is not pure water. Okay, so we have ways to test what is present in a solution, as well as testing how much of a substance is present in a solution. Now, obviously, because, again, the majority of our planet is made of water, any companies that deal with chemicals have to make sure they're disposing and storing of them in safe ways so that they don't get into our groundwater and into our environment. This is known as the Responsible Care Program. Now, this is important because, again, when you have a toxin, it dissolves in water, for example. We might not see that it's in there because the toxin dissolves. Some toxins can have immediate effects at very low concentrations. Sour gas is causing a loss of consciousness at 700 parts per million. 700 might seem like a big number, but this is parts per million. So in a million parts, 700 of them are the sour gas. And that is actually a very small concentration. Sometimes, though, concentrations or toxins at low levels are not toxic, but they build up in the food chain. If you remember this from Science 10, Science 9, if you're in Bio 20, this is called bioaccumulation or biomagnification, where compounds, heavy metals like mercury, lead, arsenic, PCBs from plastic, DDTs from bug spray, at low levels and organisms low in the food chain, they only maybe ingest a small bit of the particles, but then the next organism eats a bunch of those. That organism eats a bunch of those, and so on until you get to the organism at the top of the food chain, and they have a huge amount of that toxin in them. Okay, so this is known as biomagnification. It's the increase in concentration of toxins as you move up the food chain. Okay, so we obviously have to be very careful when we are doing any type of industrial processes that do maybe create some toxins, that we're being careful that we're disposing of them and storing of them in very safe ways. So we must assess our risks and benefits of using the substances. Okay, let's get into how do we calculate concentration. So concentration tells us the amount of solute relative to the amount of solvent. I could tell you that you have a dilute solution, which means that there is very low solute and a high amount of solvent, or I could tell you you have a concentrated solution, which would actually have a lot more solutes, still more solvents than solutes, but it's very, very, very highly concentrated. Okay? Now, there are a variety of ways of expressing concentration. I don't teach all of these different ways. You learn a lot of them in Science 9. I'm going to focus in my class on moles per liter. That is the standard way of measuring concentration, as well as sometimes millimoles per liter. But in Chem 20, moles per liter is what we focus on. I'll briefly mention the other ones and some examples, but ppm again stands for parts per million, ppb stands for parts per billion, ppt stands for parts per trillion. You can have percent mass where it gives you a percentage and then has a WW after it, which means weight per weight. You can have a percent volume, which again gives you a percent and then says V per V. Or you could have just a percent by itself, or megagrams per deciliter. Now, I do have a question on my test for my students where they are given a list of ways of expressing concentration and asked which one of them is not one of the ways of expressing them. So you do need to know these ways, but I don't teach, again, how to do all those calculations. We're going to focus on moles per liter. Okay, so some examples again, vinegar is given a 5% volume per volume. Toothpaste is given a percent weight by weight. Blood cholesterol levels are milligrams per deciliter. And a breathalyzer gives you a decimal place which represents a percentage. Okay, so let's get into our calculation, molar concentration. So sometimes you might be asked to calculate the molar concentration, or you could be asked to calculate the molarity, okay? So molarity stands for molar concentration, where you are taking the number of moles and dividing by the liters of solvent. Okay, so in other words, I'm taking my N, which is my number of moles, and dividing by my V in liters to get my volume. Okay, now N is also sometimes needed to be found again with mass over molar mass, like we learned in Science 10. Now again, formulas are not given, you have to memorize them. I like to memorize formulas in a linear format. So I would memorize that N equals C times V. So if I'm solving for C or V, I divide by the other. And then mass is moles times molar mass. Okay? You could also, when you have a 3-variable formula, you could use this triangle method. So my triangle method would be C equals N over V. So if I'm solving for C, my N is above my V, so it's N over V. If I'm solving for V, my N is above my C, so it's N over C. And then if I'm solving for N, the C and V are side by side, so it's C times V. Okay? That helps some students that struggle a little bit with rearranging formulas. You could do the same thing with the mole and molar mass formula, where you have N equals mass over molar mass. Okay? So again, if we were to, I'm just going to erase this so that the formulas can pop up here from my PowerPoint presentation. Our concentration is going to be in moles per liter, right? Because my units of N is mole, my unit for volume is liter, and needs to be in liter. Okay, so if you have a volume in milliliters, a milliliter, again, some of you know I just divide by 1,000, and that converts it into a liter. Okay, but if you are unsure, and maybe you have something like a megaliter or a picoliter, then you use the SI prefix. It's on the data booklet. It tells you that a milli is equivalent to 10 to the negative 3. So you take that value and multiply by 10 to the negative 3. Okay, that's the same thing as dividing by 1,000, but that's what you do when you have an SI prefix that perhaps you're not familiar with. Mass needs to be in grams, and molar mass from the periodic table is in grams per mole. So I have quite a few examples, just practicing using these formulas. So I am given 0.900 mole. That is my N. And I am given 0.500 liters, that is my V. So this is very straightforward. My N is 0.9, my V is 0.5. They're in the units they need to be in. So I just write my formula, C equals N over V, put my values in the formula, my N divided by my V, and get an answer. Now when you get your answer, you get 1.8. But sig digs, remember leading zeros don't count, so there's 3 sig digs in the moles and 3 sig digs in the volume. So I need 3 sig digs in my answer. So when I get 1.8, I have to add a 0 to it to make it 1.80, and then my units again are moles per liter. Okay? So this was a very straightforward question where it gave you the values exactly as you need. You're just plugging them into the formula. The next example, very similar. Again, I am given moles, which is my N, but my volume is in milliliters. So I need to convert it into liters first, okay? So our N again being 0.300 mole, my volume would be 0.100 liters. And now again, I just plug them into the formula, C equals N over V. Again, my N was 0.300. My V is 0.100 liters. Notice again how our units are moles over liter when we get our answer. Now when you get your answer, you get an answer of 3, but we need to add 0.00 to again have 3 significant digits in our answer matching the numbers in the question. And the units again are moles per liter. Okay, so another pretty straightforward question, just making sure you convert your volume from milliliters into liters. The next example gets a little tougher. I have a volume in milliliters, which again, not a problem. We can divide by 1,000 and convert it into liters. But I am given a grams, which is a mass. Okay, so what that means is I need to, again, if I'm asked for molar concentration, that's concentration in units of moles per liter. I need to know how many moles I have. So we're going to have to use the formula N equals mass over molar mass. Okay? Now I am given the formula of my solute. If I was given the name of my solute, sodium chloride, remember this is ionic, I would need to balance the ion charges to write the formula so I know how many sodiums and how many chlorides there are to find my molar mass. Our molar mass would be 1 sodium and 1 chloride, so it would add up to 58.44 grams per mole. Remember again, sodium is 22.99 and chloride is 35.45. So that adds up to the 58.44. So if I find my moles first with mass over molar mass, I have 3.2 grams divided by 58.44 grams per mole. Remember, when you have a denominator in the denominator, it actually moves up and becomes part of the numerator. So my grams cancel and I'm left with moles on top. So my answer, I leave it unrounded. I write a few digits down and put dot, 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 saying that I'm using this complete unrounded answer in my next calculation. So to find my C, I now take this unrounded answer, leave it stored in my calculator the way it is, and divide it by my volume in liters of 0.250, and I get an answer, again, in moles per liter. When I look back up at the question, there's 2 digits and 3 digits. The lower are 2, so I can only have 2 digits in my answer. I think when you do this calculation, let me just do it really quickly. 3.2 divided by 58.44 divided by 0.25. Yes, we get an answer for our C of 0.2190, so on. Remember, when you're keeping your sig digs, you always look at the digit you're cutting off. If it's a 5 or more, it rounds the last digit that you're keeping up. So that's why it becomes 0.22 moles per liter. Okay? And that is example 3. We have a couple more examples. Example 4 asks us to calculate the number of moles. So we are looking for N. I am given a volume again in milliliters, so I need to divide by 1,000 to convert it into liters. And we are given a number of moles per liter. That is our concentration. So our concentration, or our C, is 1.25 moles per liter. Our V is 0.500 liters, and we are looking for N. So that formula to solve for N is C times V. Okay? So I put my concentration and my volume in. Now this moles per liter really means the liter is on the bottom. So the liter would cancel with the liter, leaving us with moles on the top. So if I do that calculation, I get an answer of 0.625. I think that's the exact answer. That has the proper sig digs, 3 digits, leading zeros don't count, so those are my 3 digits. And the units again are mole. So 0.625 mole. Okay, next example, how many liters? It is asking us for volume. We are again given a number in moles per liter, that is our concentration, and we are given a number measured by mole, which is our N. So if we list everything, our C is 4.22 moles per liter, our N is 3.69 moles per liter, and we are looking for V. Now the formula, again, if you're using the triangle method, C equals N over V. When I'm solving for V, it would be N over C. Or if you memorize the formula N equals C times V, I'm solving for V, so I divide both sides by C. So V equals N over C, okay? So now when I put my numbers into my formula, I have 3.69 moles divided by 4.22 moles per liter. That liter, again, in the denominator position would move back up to the numerator. So our moles cancel and we're left with liters on the top. We get an answer of 0.874 liters. Now if I do this calculation, 3.69 divided by 4.22, we get an answer of 0.8744, so on. When I'm keeping my 3 sig digs, I'm cutting off a 4, so it does not round the last digit I'm keeping up. So it stays at 0.874 liters. Again, there was 3 sig digs in my 2 numbers given. Leading zeros don't count, so those are my 3 sig digs. And again, my units are liters. Okay, the last example that we have is very important for the next lesson when we learn how to make a solution. When we make a solution, we need to know what mass of our solute, the salt just means ionic compound or solute, is being required to prepare a solution. We are preparing a solution with a volume of 1.50 liters and a concentration of 0.565 moles per liter. This is my solute. Again, if you were given the name potassium phosphate, I would need to balance my ion charges, so I know that there would be 3 potassiums bonding with 1 phosphate. So for finding my molar mass, I have 3 potassiums, 39.10, plus 1 phosphorus, which is 30.97, plus 4 oxygens, which are 16.00. Okay? So if I list my variables, again, my concentration, my C is 0.565 moles per liter, my V is 1.50 liters, and my molar mass, when you calculate that, is 212.27. So now, how am I going to find mass? My mass is going to come from moles times molar mass. I have the molar mass, but I don't have the moles. But I do have a concentration and volume. So I can find my moles with C times V. Okay? So we're going to do that first. Find our moles with C times V. So our concentration times volume is going to give us that moles. Then I take that unrounded answer, multiply by my molar mass. Again, for my units, the liters cancel because that was on the bottom. The moles cancel because that was on the bottom. So my final answer is in grams, 180 grams. Now I believe when we do this calculation, 0.565 times 1.5 times 212.27, we get an unrounded answer of 179.8, so on. I'm keeping 3 digits. I'm cutting an 8 off. Now, the 9 has to turn to a 0 and bump this up to an 8. You only bump it up if you're cutting off or if you're rounding up a 9. So the answer mass is 180 grams. And that's it for this lesson. Thank you for watching.